A very common problem in mathematics is to determine whether a given function f is increasing, decreasing, strictly increasing, or strictly decreasing. For example, let's say that I have a function f which is defined by the formula f of x is x raised to 3, and I want to determine if this is an increasing function. The answer to this question is yes, this function is even strictly increasing, but let's for the moment focus on whether it's increasing or not. Since x to the 3 is defined for any real number x, the domain of this function is the collection of all real numbers. We do have a definition for strictly increasing. The definition says that for any two real numbers, x0 and x1, where x1 is greater than x0, it must be the case that f of x1 is greater than or equal to f of x0. The problem with this definition is that it's very difficult in general to check if a function is increasing by verifying if this holds. In order to verify that this function is indeed increasing, I have to show that whenever x1 is greater than x0, I have to show that f of x1 is greater than or equal to f of x0, which means that I have to show that x1 to the 3 is always greater than or equal to x0 to the 3 if x1 is greater than x0. That can certainly be done, but it's not a simple thing to do. A very common way of checking if a function is increasing is simply to look at the graph of the function. Here is a graph of the function x to the 3, so y is equal to x to the 3. We can see from the graph that this is indeed an increasing function. But it's hard to argue that this function is increasing simply because my eyes tell me that it's increasing. An additional problem is that we can only draw a graph for a certain domain, in this case from -2 to 2. And it is possible that the function does something weird outside this domain like this, in which case it would not be an increasing function. In this case, it will not do that, it will keep on increasing, but you get the point. It's hard to argue that a function is increasing or decreasing just based on a picture. The picture can help us figuring out if the function is increasing, but we need a more formal way of actually showing that it is increasing. Fortunately, we have the following very nice result. If f is a differentiable function, that means that you should be able to find the tangent for any x in the domain of the function. Then, if the derivative is greater than or equal to 0 for all x in the domain of the function, then f is increasing. The reverse to this statement is also true. So if f is increasing, then the derivative is greater than or equal to 0 for all x in the domain of the function. This is a super useful result because it makes it very simple to check if a function is increasing whenever the function is differentiable. All we need to do is to take the derivative and check that the derivative can never be negative. To go back to our example, if f of x is x to the 3, then we know that the derivative is 3x squared. Since x squared can never be negative, it follows that this one is always greater than or equal to 0, which proves that f is indeed increasing, consistent with the conclusion we drew from looking at the graph. We are not going to prove this result, but just spend some time thinking about this yourself. If the derivative is greater than or equal to 0 everywhere, it means that every tangent will slope upwards or it will be horizontal. If this is the case, then the function must be increasing. Vice versa, pick any point on an increasing function, and I hope it makes sense to you that the tangent at this point must slope upwards or be a horizontal line. We also have the following. If the derivative is less than or equal to 0 everywhere in the domain, this is equivalent to f is decreasing. Let's move on to f being strictly increasing or strictly decreasing. Here we have the following result. If f prime x is strictly greater than 0 everywhere in the domain, it will then follow that f is strictly increasing. Here, it's super important that the implication only goes from the left to the right. It does not go from the right to the left. This means that if f is strictly increasing, it will not follow that the derivative is strictly positive everywhere. But let's get back to that point in just a little bit. So let's say I have a function f of x equal to e to the x. This function will be strictly increasing. How do I prove that? Well, all I have to do is to find the derivative. The derivative to e to the x is just e to the x. We know that this is strictly positive. A power with a strictly positive base must be strictly positive no matter what the exponent is. So the exponential function is indeed strictly increasing. A second example will illustrate why we can go from the left to the right, but not from the right to the left. So my f of x is x to the 3. If we go back and look at the graph of x to the 3, then you may be able to convince yourself that this is strictly increasing. We know that f of 0 is 0, 0 to the 3 is 0. But if you plug in any value which is slightly bigger than 0, doesn't matter how much bigger, then this will become greater than 0. If you plug in a value slightly less than 0, then this will become negative. So if you pick 2 points, x0 and x1, where x1 is to the right of x0, then x1 cube will always be bigger than x0 cube. Try it yourself with a couple of numbers. As I mentioned before, proving this formally is a little bit messy. However, when we go to the derivative, then we see that the derivative f prime x is 3x squared. The problem here is that the derivative at x equal to 0 is 0, and this is not strictly bigger than 0. So we have here an example of a function that is strictly increasing, but the derivative is not strictly positive everywhere. So this raises the question, how do you then determine if a function is strictly increasing? Well, you can do the following. If we look at a sign diagram of f prime x, the sign of the derivative when f of x is x to the 3. F prime x is 3x squared. That means that when x is 0, the derivative is 0. When x is positive, then 3x squared is positive, so the derivative is positive all the way up to infinity. If we go to the left of 0, when x is negative, x squared will be strictly positive, so the derivative is strictly positive here as well, all the way to minus infinity. So here is the rule. If the derivative is strictly positive everywhere, with the exception of one or several isolated points, like this one, where it's equal to 0, then it is still strictly increasing. It's important that it's just an isolated point where the derivative is 0. If the derivative is 0 on an entire interval, then it cannot be strictly increasing, just increasing. And if you find any point where the derivative is actually negative, then again, it cannot be strictly increasing. We also have if f prime x is strictly less than 0 for all x values in the domain, it will follow that f is strictly decreasing. But the opposite is false. A function can be strictly decreasing and still have isolated points where the derivative is 0, not a problem.